Hello and welcome to Sunday's edition of Cracking the Cryptic, and we've got a tenaliraman puzzle for you today. Tenaliraman being, I think, one of the best and most consistent setters on the world scene. He seems to produce about a puzzle a week of stunning quality, and this one is called The Knot. I do not know why. I have had a quick look at the grid to see if I can see why it should be called The Knot. I can't see any reason, but maybe the solve will reveal all. Now, before I read you the rules, a couple of things to mention. Firstly, we've got my solve of PHISTOMEFEL'S new logic puzzle, Sisyphus, available for patrons of the channel over on Patreon at the moment. It's a very interesting puzzle involving rolling rocks into the grid. I definitely recommend it. I'm also planning, by the way, to have a go at a snooker-themed puzzle by Apio. It's basically to celebrate the fact that the World Snooker Championship has started in Sheffield yesterday. I'm quite a big fan of snooker for some sin I must have committed in a former life. I noticed Apio has published a World Snooker Championship themed puzzle on Logic Masters Germany. So it's got the reason I'm not going to do it on the channel is it's got an enormous rule set, even bigger than yesterday's puzzle. So I think I might do that as a Patreon bonus, unless you guys tell me otherwise. Anyway, that's all I've got. The other thing I'd just mention, which is a bit of a secret, is that we have some very interesting stuff coming up on the channel in the coming days. Very interesting indeed. I'm not allowed to say any more about that. Anyway, what are the rules of this one? There are 9 cell regions in the grid. Gosh, I think that's the first puzzle, or at least Sudoku puzzle in a while. I haven't started with normal Sudoku rules apply. So here we're saying there are 9 cell regions in the grid. Each region contains each digit from 1 to 9 exactly once. And each row and column can also contain the digits from 1 to 9 exactly once. Okay, so this is just saying this is an irregular Sudoku. So you can see, in fact, that box is the same as normal Sudoku. This box, on the other hand, most certainly isn't. So there are a few boxes in this Sudoku. They're all of size 9, but they're definitely not square 3x3 boxes. So we've got to make sure we've got 1 to 9 in each row, in each column, and in each weird region. That's basically what we've got to do. The digits on the arrow path add up to the digit in the arrow circle, and digits on an arrow may repeat if allowed by the other rules. So normal arrow rules as well. If you've not come across arrows before, let's look at this arrow here. That means you add up whatever you put in those 3 squares. Let's say you put 2, 3, and 4 in. This square would have to be a 9. 2 plus 3 plus 4 equals 9. There is a knowledge bomb from Cracking the Cryptic. We're so generous with those. Anyway, do have a go at this. The way to play is to click the link under the video as usual. Now, I'll put my glasses into position. I'll have a go. Let's get cracking. So, what do I see? The first thing I see is not this arrow, actually, although that is a little bit interesting. Actually, no, I tell a lie. That is not interesting. I'm going to relegate this arrow to the status of uninteresting because, well, you could certainly repeat 1 on this arrow. Those two could both be 1. That could be a 2, so this could be a 4. And knowing that this digit is a 4 or higher is really not very helpful. You can't put 3 1s on that arrow because those two would be in the same box of the Sudoku. So 3 is not an option, although it might have looked at first blush like it was. But I can see in row 1, look, I've got 5 cells in the same row there. So what's the minimum I could put on those arrow cells? 1 plus 2 plus 3 plus 4 plus 5 is 15. Now, therefore, those circles must be selected from 6, 7s, 8s, and 9s. If I try to put, for example, a 5 in there, I'd have to put a 10 in there, and that won't work. So, there's a small deduction we've got going on there. Now, what else can I see? Right, same thing in column 5. I've got 5 arrow cells here that are emerging from just 2 circles. So these 5 cells have a minimum value of 15. So those squares have to be at least equal to 6. Got to be a little bit careful there. Often when you get this arrangement, these circles will be in the same row as they are here. Here we could repeat a digit, so we could have 8 in there, for example. We've got 5 cells in row 5 in the same on arrows in the same row. So again, those two squares have got to be 6, 7, 8, and 9. Right, I see what's going on here. Right, this is lovely actually. We're going to get a chance to look at the geometry very early, because here's the big reveal. Those two cells contain the same digit. How do we know this? Well, this is the most important trick if ever you are faced with irregular Sudoku. Sometimes it's called the law of leftovers, but the way to get your head around it is to think about, in this instance anyway, the bottom 4 rows of the grid. Now let's imagine we had a time machine and we warped forward in time, and hopefully we would discover that I had completed the puzzle correctly. Now if we did that, what digits would we find in the yellow cells? Well, we don't know the order of the digits, but we do know exactly what those digits would be, because this row needs to have the digits 1 to 9 once each. So does this row, so does this row, and so does this row. So these yellow cells in the correct solution will be 4 sets of the digits 1 to 9. Well, there's one set of the digits 1 to 9. There's another set of the digits 1 to 9. There's another set of the digits 1 to 9. So that's 3 complete sets of the digits 1 to 9. And if we look at this region here, look, those squares, just these squares here, they've all got to be different digits because they're all in the same region of the Sudoku. So that's 8 of the digits 1 to 9, and it's just missing 1 digit. Well, that's that digit then. That digit must be the final digit that we need to make sure that the bottom 4 rows contain all of the digits from 1 to 9. But that square, look, therefore must be the same as that one, QED. So these I'm going to colour. Now, in the course of explaining that, I have noticed something I should have seen immediately, which is that the same thing is going on with the last 4 columns of the grid this time. In fact, it's absolutely identical in terms of its almost symmetrical cages as well. So again, we know that the final 4 columns must contain 4 sets of the digits 1 to 9 in the correct solution. That's 1 set, that's 2 sets, that's 3 sets. That's 8 of the 9 digits we need in the final 4th set. So the final digit that we know must appear in the last 4 columns must be, sorry, I need to have that one as well. That makes the 8 digits. Must be this square that's sticking out. So this square needs to be replenished, if you like, by this box lending that digit into the final 4 columns. So those squares are also the same. Now, yeah, that's actually really a beautiful idea. It's quite simple, but yeah, if those squares add up to at least 15, and they do, but these are the same digit, can these be double 6 or double 7? Well, the answer is no, because 12 and 14 is less than 15. So we can remove 6 and 7 from there, and presumably we can remove 6 and 7 from there for the same reasons. Once we know that those yellow squares add up to at least 15, we can't make these double 6 or double 7. So now we've got 8, 9 pairs all of a sudden in row 6 and column 6. And we now know that arrows add up to an even total, because they're either adding up to 16 or 18, depending on whether this is double 8 or double 9. Now, I'm tempted to try and colour more squares in. I don't know whether what we're meant to do here is to try to maybe work the arrows harder or to work the Sudoku harder. Let me just have a stare at this for a second. Right, okay. I can see something about this box. So where does red go in that box? Well, by Sudoku, red is not in those squares. Red is not blue, so it's not in this square. Well, can we put red on a 3-cell arrow? No. Even if red is 8, if I put 8 here and make this 9, these two squares would have to sum up to 1. That's impossible. So red is ruled out of all 8 squares there, and that must be red. Now, I wonder if we can... Oh, no, hang on. I was about to wonder whether we could do the same with blue, but I'm going to not wonder that yet. I'm going to look at row 1. Because if I know that these add up to at least 15, and I do, but this square is an 8 or a 9, that feels like it's... That feels like it's important. Hang on, how can I use that? One of these now is going to have to be blue. Do I know which one? And that's because if neither of them is blue, then axiomatically they would be a 6-7 pair, and 6 and 7 only add up to 13, which is not 15. Now, hang on a second. Blue is in one of those squares, but I don't know which one. Oh, look, I see what's going on. This is remarkably clever. Okay, we can do more with blue. In fact, I think this square is blue, but the reason this square is blue is not to do particularly with row 1. It's to do with this region here, and where blue goes in it. Because blue can't go in those squares. It can't go in this square by our old friend Sudoku, and it can't go on a 3-cell arrow because there's no way, even if blue is 8 and red is 9, you can't make the other two squares add to 1 again. So it's the same logic, it's just a slightly different shaped box. But basically I think this square is blue in box, whatever box that is, the equivalent, maybe it's the equivalent of box 4, but maybe it's not. But anyway, that square is blue, and that means this square... Well, there's a couple of ways of looking at this. This square now sees a red and a blue square, so it sees an 8-9 pair somehow. So that's a 6 or a 7, and once this is a 6 or a 7, we know that that square now has to be blue, because we know these two have to add up to at least 15. Now, blue in this box is... no, oh, hang on. Yeah, blue in... That's blue, isn't it? So blue in this box is in one of those two cells. Maybe red in this box? No. Red in this box? No. Okay. Oh, blue in this box then. So blue's in one of those 3 squares, which means blue is not in any of those squares or this square. So blues are in those 2 squares, I think. Oh, does that mean this is blue? I think it does, because there's a blue in one of those 2 by Sudoku, so this is not blue. So now this square is an 8 or a 9. And I think there seems to be quite a lot we can do here, even with these oddly positioned reds and blues. Sorry, let me just take a think about this for a second. Presumably, no, okay. 15. This is interesting actually. I can narrow down the value of this square just using maths, I think. And this is because of the secret, which is the secret, of course, that we tell people very occasionally if they're very lucky, is that the correct solution will, well, if we looked at the correct solution, row 1 would contain all of the digits from 1 to 9 once each. If you add up the digits 1 to 9, you get 45. So this row adds up to 45. It's actually not as straightforward though, is it? Although I know those are adding up to 17, I don't know what these arrows add up to. So I could limit this square, but I don't think it's naturally easy to limit it. No, because this could be 8, 7, or that could be 9, 6. or it could be 9, 7. There's a few different ways of doing it. Sorry, I think I'm getting sidetracked here. What is it I'm meant to be looking at? We can... don't know. Don't know. Maybe it's better to do maths on column 5, actually. Yeah, that's a good thought. Okay, let's look at column 5 instead. Because I've got an 8 and a 9 there, so that's these two squares definitely add up to 17. And then the arrow cells, look, have two possible options. They either add up to 16 or they add up to 18. So these cells together either add up to 17 plus 16. They either add up to 33 or 35. So these two squares either add up to 10 or to 12. This is weird. Okay, so these two squares either add up to 10 or to 12, but then the same thing is going on in row 5, look, because those two squares add up to 17, but depending on what red is, the arrows are adding up to either 16 or 18 again, so it's exactly the same logic. So oh, I see. Is it this arrow that... Is this... I think I found out why this is called the knot. I think it's... Oh, this is lovely if it is. I think it's that. That is the knot. Imagine that was a piece of string going round and we were tying it in a knot. I think... Depending on which number red and blue are, one of these is adding up to 10, the other is adding up to 12. But look, these are this arrow shape here has connected these together, so that this square is definitely higher than this square. Because in its sum, it includes this square. This little arrow is reflecting into this square here. And that is part of the sum of this square. Oh, this is a double 1. That is a double 1. That's what we can do from that. Because we know that the difference... But what we know, one of these is adding to 10, one of them is adding to 12. So the difference between 10 and 12 is 2, and that 2 has to be made up by these two squares on this arrow. I think I've jumped a few steps there, so we'll do this slowly. But I think it's right. I haven't quite worked out what the middle square is yet, but I think I probably could if I thought about it for a second. Let us just try and get a handle on what is going on here. Now, what is the easy way of explaining this? This is, it's quite a beautiful pattern, I have to say. It's another original idea from Tenaliraman, this thing going round and... But basically, yeah, whatever this is, let's imagine this square was a 4, just for the sake of argument. This square would be a 4. Now you can see now that we've got to add something to 4 in order to get to this square. So this square is definitely higher than 4, and it's at least 6, so it could be, in fact, 6 or 7. But we know that one of these pairs is adding up to 10, the other one is adding up to 12, but they share this digit. So whatever goes into this square, you can see because this is higher, this one has to be the one that adds up to 12. So in this situation, In fact, you can't make it work. So we just prove this is not a 4. Because how could it be a 4? In order to make this one add up to 10, you'd have to put a 6 here. And in order to make this one add up to 12, you'd have to put a 6 here. And that is not going... Oh, where's my ability to put 6 gone? That won't work. But you can... Hopefully you're now seeing why I think this has to be double 1. Because I know that the difference between this sum and this sum is 2. And that difference is represented in those two squares. So can we do this a bit more structured? I'm just trying to think if there's a quick way of narrowing down this square here. We can... Hang on. If we've definitely got to have 16 or 18... Right, yeah, okay. We've got to have 1 and 2 on these arrows, haven't we? Because there's no way of making a 16 or an 18 total in 5 different digits unless you use a 1 and a 2. And the way to figure that out is to know your triangular numbers. If you know the triangular number for 6, i.e. what's 1 plus 2 plus 3 plus 4 plus 5 plus 6, you will get 21. So if you were to miss out a 1 from 5 digits, then the minimum you'll get is 21 minus 1, which is 20, which is definitely higher than 18. So we know there's a 1 and a 2. Similarly, because 21 minus 2 is 19, that's still too high. Same thing must be true down here. So this square here now, which we know is 2 less than this square here, can be 3, 4, or 5. That's the only options, because this cannot be higher than 7. So this is now 5, 6, or 7. This is 3, 4, or 5. We already proved that 4 didn't work, didn't we? So we know these two are adding up to 12. So we can see that this is 5, 7, or 6. We know it can't be 6 because that's going to double the 6. Oh, it's so lovely, isn't it? Once this can't be 6, remember we were removing 4 from here. How can 5 go in the middle of the grid? It can't, because 5... Because we know these would be adding up to 10, they'd have to be double 5. That won't work. So this is 7, this is 5, this is 3. Now these are adding up to 10, these are adding up to 12, and all is well in the world. We have, I think, now finished at least that part of the puzzle. Now there's no 1 in those two squares. There's no 1 here. There's... What else? Oh, I suppose what we now know is... Yes, we must know what red is, and we must know what blue is. And the reason we must know that is that we know that red has to be higher than blue, because we know that these two squares are lower, if you like, than what we've got along the arrows. If we only need 10 more to complete the 45 in this row, the reds are going to have to be higher than in this column where we needed 7 and 5 to complete the 45 total. So those are 9s, these are 8s. Whoopsie. Blue is 8 now, so all of these become 8. This becomes a 9, and we're slowly but surely igniting the flame, I think. Now, can we keep this going? We can... Oh, yeah, I can get that square straight away now, because 6 plus 8 is 14, and that's not enough for 5 cells in the same row. So that must be a 7. And now we know these squares here are a 1, 2, 3, 4, and 5 combination in some order. So we get that square, which is a 6, to complete the row. Can we get any more? 3 by our old friend Sudoku appears in 2 cells in what I'll call box 9. And okay, I think now we're probably going to have to start thinking harder again. What, if anything, is obvious here? Oh, I tell you what is obvious. Where does 6 go in column 5? Well, you can't put 6 on an 8 arrow of 3 cells, so it must go here, and therefore that's a 2, 6 pair. Those squares are going to have to be 1, 3 and 4. So these 3 squares now have got to be 2, 5 and 7 to complete this box. That's not a 2 anymore. Now, what else can we do here? 2, 5, 7 here. Do I know what... Can I do the same thing in this row? Do I know where... Oh no, the thing is 6 could be on the 9 arrow, so maybe I can't do the same thing. Do I know this? No, I don't know there's a 2 in here. This is all part of my 1s and 2s pencil marking, which I think I'm going to have to remove now for fear of making an error. So this 9 arrow in 2 cells is not 3, 6 or 2, 7, so it's 4, 5 or 1... Ah, it's not 1, 8. Oh yeah, okay, this is where we should look. That has to be a 4, 5 pair, because it can't be 1, 8, 2, 7 or 3, 6. So these squares are 1, 2 and 6 to complete. Oh, yeah, these 3 are 1, 2 and 6 to make 9 work, and I've got 2 and 6 already in this column, so that squares a 1. We get a 2, 6 pair here. These squares have now got to be 3, 4 and 5, I think. Which means that square is a 1, lovely. This square is not a 5. This arrow is absolutely, it almost looks broken. It's not quite, thank goodness. But that definitely can't be a 5 because I can't put 0 here. And it definitely can't be a 7 because I can't put a negative number here. So that square is a 2. That's a 7, that's a 5. This square here... don't know that we know what this is. Well, I can see it's got to be 1, 2 or 3. I'm wondering if I can see which of those it has to be. But no, I'm not sure. No, sorry. All right, let's look somewhere else. Where else can we look? We can... That square's restricted now. Oh yeah, that square is restricted. This circle sees 9, 8 and 7, so it's got a maximum value of 6. Oh, and you can't put a 1 on it. The ones here mean this... Hang on, so what can this be? That can be 5 or 6. It can't be 4 because you'd have to go double 2. That won't work given you can't use a 1 on the arrow. So this is a 5 or a 6. It's definitely got a 2 on the arrow then. And it's either 2, 3, 4... Sorry, 2, 3 or 2 and 4. That square is not 4. What? No, that square, that's not right, Simon. That's this square can be a number of things that are not impacted yet by this. Do not worry about this square at this point. I think we don't know. But... Ooh, now here's some nice logic. How many 2s are there in the correct solution to this puzzle in row 7? The answer is not a trick question. 1. How many 2s are there in row 8 in the correct solution? 1. So, but look, we know that there's a 2 in one of those squares, so that's one of those 2s. There's a 2 in one of those squares, so that's the second 2. So you can't put any more 2s in row 7 and row 8. So where does the 2 go in what? Well, this box 9 area. It's got to go in the bottom of the... Oh, it's got to go in row 9. It's got to go in one of those 3 squares. But now look, if my pencil marking is right, this 2-cell arrow here cannot include a 1, a 2 or a 3. So there's only one way we can make that work, and that's with a 4, 5 pair and a 9. Which means that's not 4. Oh, not 4. Now, what does that do? The answer is not clear yet. It means, well, that's red, isn't it? So 9 has to be in one of those 2 cells. 9. Still don't think we know enough about 9 to be able to place it anywhere else. I'm probably missing something there. Bobbins. Okay, so let's have another stare. What is it we're what is it we should be looking at? Perhaps the bottom of this column. We need 3s, 4s and 8s into those squares. Maybe this one is the key. 3, 4, 8. Oh, okay, so where does 1 go in this box? That's a sensible question. It's got to go there, and that's got to be a 9, and therefore this square is known and has to be a 7. That's important. In fact, this whole thing is important, because now this arrow can only start with an 8, given it's got a 7 on it. That square's got to be a 1 to make the arrow add up. That square's no longer a 1, which means this square's no longer a 3. That square's no longer a 1. This square's no longer a 1. Oh, which I think we knew already if I thought about this 7 total. Oh yeah, we did know that already. I just hadn't looked at it. So, okay. Can we just... we must be able to do all the 1s now, surely. Where does the 1 go in this region? It's got to be in one of those 2 squares. Where does the 1 go in this region? Maybe this region? It's got to be in one of those 2 squares. And the 1 in that region has to be... oh yeah, hang on. We've got those 2 1s. There has to be a 1 on the 8 arrow, so that's got to be a 1. That means this is a 1. And now we must be able to get all the 1s. Yeah, we can. Okay, so all the 1s are filled in. This column needs 2, 3, 4, 5 and 6. We know this is not a 2 or a 3, so this square is a 4, 5 or a 6. Can't see whether that's resolved. It might be, but it doesn't seem to be immediately obvious how. So where else should we look? We've got a 3, 4, 5 triple here, so we actually know what these squares are. These have got to be 2, 6 and 9. Well, you can't put 9 on an arrow. You can't put 9 in the square that's already seeing a 9 in its column, so that becomes a 9. That's lovely. That places 9 in a circle in box, what I'll call box 3. This square now has got to be 7, if this is a 2, or 3. 3 or 7. Oh, which we can resolve if we fully pencil mark this box, because that is a 7-8 pair. Look, just to complete the digits that we've not filled in yet in this box. Maybe is this box 6? I don't know. That square's a 3 though. That gets us the 6 here. That places a 2. This 3 is going to sort out that this 8 arrow must be 2, 5 to finish it off, which means that becomes a 3, 4 pair. Now, there's a 4, 5 pair in column 8 I hadn't noticed, but it doesn't see anything. So that's a bit annoying. Those squares have got to be 6, 7 and 4. Oh, misclicked, sorry. That one can't be 4. 4, 6, 7 though sees this 3, so that's a 3, that's a 4. This 3 is seeing this square, making it a 2. There was a repeated 2 on this arrow, which places a 4 here. This 2 is placing the 2 and the 6. That's no longer a 6. 3, 4, 5, 4 here. That gives us the 4 and the 3. And can we keep this going? Maybe. We need 5, 6 and 9. That's got to be a 5 by Sudoku. This is a 6, 9 pair, which must be resolved. I don't know. How is this not resolved? How do we resolve this? Or maybe we're meant to look at... This is 6, 7, 8 and 9 down here. Maybe we can do something. I can see that can't be 8 or 9. That can't be 7. No, I'm still not quite getting to the nub of this, I don't think. Oh, we can't put 8 into those squares, so these are a 3-4 pair. There must be something disambiguating this. Oh, sounds like the police are chasing me down, probably because I've been too slow at solving this Sudoku. Okay. Right, where is the next deduction to be had? This 4 is giving us a 5 here. There's a simple deduction. Yeah, that actually is worthy of being arrested by the police, not spotting that this 5 was resolved because of the 4 here. Apologies, that gives us a 6. That's a 2, that's a 4. Lovely, that gives me the 4 and the 3. This 6 is resolving the 6 and the 9, which feels like, oh, that is important, look. So now we're down to an 8-9 pair here, and we know that this square has to be a 3. That 3 places a 3 over here if we trust our pencil marks, and why wouldn't we? That's 2 and 6 is resolved by the 2 in this square. And now this row, oh, this 9 here is resolving everything. Look, 9 and 8 go into those 2 squares. We need 5 and 6 into these 2. This 4-5 pair resolves it. 6 and 5 go in. The 6 sees this 7. I think we're on the home straight now. Probably famous last words, but it does seem to be slowly going in our favour. And this box down here needs 2, 7 and 8. That's got to be a 7 in the corner. And a 2-8 pair to finish this box off, which means this square is a 6. That 6 sees the 4 and the 6 at the top. And, okay, what do we need to finish this box then? 2 4s and 7s. So that's a 4. That's finishing the 4 and the 5. This is a 2-7 pair, which must be resolved. Oh, it's this 5 that's resolving everything. There you go. 2s and the 8s go in. 8s and the 7s go in. The 5 and the 4 goes in. And that is another beautiful tenaliraman puzzle. Loved it. Absolutely loved it. The idea of this knot and the linkage provided by this funny arrows series here is really stunning. It's just an original idea executed with such aplomb again. Loved it. Let me know in the comments how you got on, and we'll be back later with another edition of Cracking the Cryptic.